recorded. Session is being recorded. Awesome. So on Tuesday, we were talking about binomial distribution, right? Yeah, I gave you an example. The procedure rolling a die 10 times is a binomial distribution. If we let x, here x is a discrete random variable. If we let x to represent the number of successes in the 10 trials, we assign getting number 6 as success. Then x would be binomial distributed. So that's what we have learned on Tuesday. We gave the 4 conditions for a procedure to be a binomial distribution. We finished the table and know the formulas to calculate the probability of the variable assume each value. And how do we find the mean and the standard deviation for the variable? So we're going to look at this formula. Suppose x follows binomial distribution. There are 2 important parameters in a binomial distribution, n and p. N and p are the only 2 parameters that matter in a binomial distribution. N here is the number of trials. N here is the number of trials. We roll a die 10 times, then n equals 10 in this case. And p here is the probability of success. That probability remains the same in all 10 trials. Since in our procedure, success is defined as getting number 6, so the probability of getting a success result or probability getting number 6 would be 1/6. So in our case, n equals 10, p equals 1/6. N equals 10, p equals 1/6. And multiply the 2 numbers together. Simply multiply or take the product of the 2 parameters together. We would have the mean we are looking for. Just multiply n and p. So 10 times 1/6. 10/6 or 5/3. Yeah, that is the mean. And the sigma here represents the standard deviation of x. How do we find the value for the sigma? We use this formula, square root of NPQ. Yeah, you can use your calculator. Multiply n and p and q, and then take the square root of their product. Question, if p equals 1/6, what's the value of q? If p equals 1/, oh yeah, exactly. Thank you, Kelly. Exactly, correct, Leah. Yeah, p and q are add up to 1 because p is the probability of success, q is the probability of failure. They are complement. The 2 events are complement, so their probabilities add up to 1. Exactly. So in this case, our sigma would be square root 10 times 1/6 and then times 5/6. And then you can use the calculator to help you to find the value. All right, so we have a few questions for section 5.2. That is about the mu and the sigma. Let's give it a try. Let's see, look at number 17. assume different groups of couples use a particular method of gender selection, and each couple gives birth to one baby. This method is designed to increase the likelihood that each baby will be a girl, but assume that the method has no effect, so the probability of a girl is 0.5. Assume that the groups consist of 42 couples. Complete the parts from A to C. Part A, find the mean and the standard deviation for the number of girls in groups of 42 births. We have a binomial distribution procedure here. I don't know if you can see that. We consider the 42 couples as 42 trials. And those 42 trials are independent when it comes to giving birth a girl or boy, right? So they do not affect each other. So here we have 42 trials, so n equals 42. And each couple either have a girl or boy. We are going to let having a girl as a success. Having a girl is a success. Then what's the probability of getting a girl is given. The method does not have any effect, so the probability of success, the probability of getting a girl is still half, or 1/2. All right, do you see that this is a binomial distribution with n equals 42, p equals half? Because the 4 conditions are satisfied, I can go through the 4 conditions for you. The first condition, there is a fixed number of trials. We have 42 trials, so condition 1 is satisfied. Condition 2, the 42 trials are independent. Condition number 3, for each trial, the result or the outcomes can be divided into either success or failure. Yeah, we have exactly only 2 outcomes. If we let a girl to be success, then boy would be the failure. The fourth condition, the probability of getting a girl, the probability of getting success remains the same for all the 42 trials. Exactly. Getting girl always have a half or 50% chance for all the 42 couples. After you check all the 4 conditions, you will see this procedure is a binomial distribution. Okay. Yeah. So X here, we need to clarify what is X. X here would be the number of girls in the 42 trials, right? Yeah, I mentioned X always have to be the number of successes among the n trials. That's how, on that condition, we have X follow the binomial distribution. So X here follow binomial distribution. And the 2 parameters, n equals 42, p equals half. And the first part A, is to find the value of the mean. The value of the mean, earlier I gave you the formula. The value of mean equals the product of the 2 parameters, n times p. N is 42. P is half. Multiply them together, 21. So the mean is 21. It makes perfect sense because you have half a chance to get a girl, half a chance to get a boy, right? So among 42 births, of course, you are expecting to have 21 girls. Is consistent with our common sense here. All right. And what about the standard deviation? The standard deviation by the formula, you need to memorize that formula, okay? Standard deviation is the square root of NPQ. N is 42, P is a half, Q is a half. Q is the probability of getting boy is also half. Q must be 1 minus P. And then we have 42 over 4, and then take the square root. Okay, I give you a little time. Look at your calculator and let me know, do you have the same decimal with me for the result? Square root of 42 over 2. Sorry, over 4, my bad. My gosh. Yeah, 42 over 4. 2 times 2 is 4. Okay, you can take a 4 out because it's square root of 4 is 2. You can do root 42 over 2 as well. And let me know what you have. Use your calculator. If you need to get familiar, be friendly with your calculator, then during the test, it would be able to help you. We do have a square root on the TI-84 calculator. It's right above x squared. Right above x squared. So you want to do second x squared, and you enter 42. Square root of 42 is 6.48, and you divide by 2. We have 3.24. And the question asks us to round to 1 decimal place as needed. So we rounded it down to 3.2. Guys, do you have the same thing? Awesome, very good, very good. All right, am I clear about how do we find the mean and the standard deviation for a binomial distribution? We do need to memorize the 2 formulas.
Yes, you're clear. What's the 4th thing that needs to be true for binomial distribution?
The important thing is you know the 2 parameters, n and p. To find the mean, simply multiply n and p. To find the standard deviation, multiply n, p, and q, and then take the square root of the product, knowing q equals 1 minus p. Okay, thank you. And then we need to think about for binomial distribution. There is a way. Do you mind I erase those because I need more space? Yeah, I'm gonna erase those. So for a binomial distribution, do we have a way to calculate the following probability quickly using the TI-84 calculator? You could use the table, but the table is slower. The faster way is to use the TI-84 calculator. So we know x is a variable followed by binomial distribution with n and p given. Then can we find the probability of x assume a specific value? You know, a specific value. Let's use little x to represent the value. How do we find this type of probability? Well, how do we find the probability that x is bigger than x, or bigger than or equal to x, or the variable less than a value, or less than or equal to a value? Yeah, are we able to find those by using the TI-84 calculator? Yes, we could. Okay, I'm gonna show you how. Yeah, let's look at the part B. Use the range rule of thumb. Okay, that's not what I want. Let's see, this significant high, significant low. Yeah, we would have to find a new question. We are going to do number 11. Assume that random guesses are made for 6 multiple choice questions on a test with 5 choices for each question, so that there are n equals 6 trials, each with a probability of success given by p equals 0.2. The reason the probability of guessing correctly is 0.2 is because you have 5 choices. One of them is correct. If you guess, you would have a 1 out of 5 chance to get it right. 1 over 5 convert to decimal is 0.2. We need to find the probability of no correct answers. All right, we need to find the probability of no correct answers. Okay, so do you identify? We have a binomial distribution here. 6 trials, n equals 6. And these 6 trials are independent. For each trial, you either get a success or failure. Success means you correctly guessed the answer. Failure is you did not get the answer correctly by guessing. And the probability of guess right or probability of success is always 0.2 for all the 6 trials. So P here, so this is a binomial. N is 6, P is 0.2. Yeah, for sure, this is a binomial with N equals 6, P equals 0.2. And what are we looking for? Yeah, X is the number of successes among the 6 trials. And what are we looking for? We are looking for a probability, okay? We are looking for a probability. The probability of no correct answers is, can we use x equals 0 to represent the result that you do not guess any answers correctly? You get them all wrong. Yeah, as I mentioned on Tuesday, is a milestone that we bring in random variable to numeralize the result. So here we use the random variable x to represent the result. X equals 0 represents the event that you guessed the 6 questions and you got them all wrong, sadly. Okay, so that's how do we express the events by using x. So here we are looking for p of x equals 0. So there are 2 ways to get it done. Okay, actually 3. We have 3 methods to get it done. The first method is to use the formula, right? The formula that I mentioned at the end of Tuesday, but I don't think anybody like to use that formula. And the second way is to use the table. When you work on the assignments in MATLAB Math, they will give you the binomial probability table that you can use. Okay, so let's record the 3 numbers. N equals 6, P equals 0.2, and X equals 0. All right, so with those 3 numbers, we are able to find the probability by looking at the table. Yeah, make sure you have the 3 numbers written down on a scratch paper or something, and then we're going to look at the table together. All right, this is the table. This is the binomial probability table. On the leftmost column, we have the n, as you can see, right? N equals 2, 3, 4, 5, and so on. That's the number of trials. What's the value of n in our case? Our n equals what?
It's 6.
Yeah, our n equals 6, exactly, yeah. So we are going to look at here, all right? N equals 6, yeah. And what is our p? The first row, across the screen, the first row is the probability, okay? Yeah, as you can see is p, yeah, probability p. What is the value of p in our case? What is the value of p in our case?
0.2.
0.2, exactly. Yeah, you should be able to find the 0.2 right here. Yeah, I'm going to highlight, like bubble this column. This column has probability p equals 0.2. And remember the n equals 6. So we do this row, right? Actually, we also have to figure out what is the value of x. We want to find the probability of x assume value 0. Yeah, how do we find the 0? So as you can see, when n equals 6, we have x equals 0, 1, 2, 3, 4, 5, right? Yeah, so our x is 0, so we're gonna only do the first row. We're gonna only do the first row. So this is the row we are going to have. Am I clear about that? Yeah, when n equals 6, and we are looking for the probability of no answer is correct, so the lowercase x equals 0. So that's why we choose this row. And the intersection of this row and the column when p equals 0.2 give us a probability. Can you see what's the probability? It's pretty tiny. What is it? 0.262, right? Yeah, exactly. And that's the probability. Okay? Yeah, that's the probability. You answer 6 questions and none of them get it right. So that's the probability, 0.262. It's pretty low, right? Yeah, that means you have more than 74%, around the 74% chance at least to get one right. And what if the problem is to help us, to ask us to find the probability that you get exactly 4 questions right? How do you find it? You get exactly 4 questions right by guessing the 6 questions. Can you find the probability that you guess the 6 questions and you have exactly 4 of them guessed correctly? Can you find the probability for me, guys? Give it a try. Yeah, look at the table. X equals 4, exactly. 0.015. Exactly, awesome. So that's how do we use the table, right? What if I want you to find this probability that x is less than or equal to 3? Yeah, not always equal. It could be an inequality symbol. What if I want you to find the probability that you have at least half of the question, no, at least at the most, sorry, at the most half of the questions get it right. Yeah, you have 6 questions you guess. What's the probability that you have at the most 3 questions correctly answered by guessing? Yeah, how do we find that? All the possible values for x. All the possible values for x is 0, 1, 2, 3, 4, 5, 6, right? Yeah. When x is less than or equals 3, we have the following a few cases. 4 cases. Less than or equal to 3, including x equals 0, including x equals 1, x equals 2, and x equals 3, right? You know what? You just need to find the probability of x equals 0, probability of x equals 1, probability x equals 2, and the probability of x equals 3, and then add them all up. Let me know, am I clear about that? Suppose the probability we are looking for is not probability of x equals a specific value. Instead, is x is less than a number, or less than or equal to a number, or bigger than a number, or bigger than or equal to a number. That's how do we get it done. Just find the values fall in the interval, and then add up the corresponding probabilities. Okay? All right, now I'm going to show you how do we get it done by using calculator. All right? I would have to push away my writing pad because otherwise it will not show my calculator. It's very dark. Let me turn on the light. Calculator time, okay? And we are going to go to second verse. Second verse. Oh, sorry. First thing, turn on the calculator. First thing, turn on the calculator. Yeah, and then we go to second verse. Okay, what is verse? V-A-R-S, capital letters, is right here. Is right here. Okay, you turn on the calculator and enter second verse. Okay, yeah, second verse. Yeah, let me know. Do you see distribution? Do you see distribution? D-I-S-T-R. D-I-S-T-R. Okay, awesome, perfect. And then in the menu, yeah, you're actually looking at the menu because distribution is the first one. And we have a normal PDF, normal CDF. Oh, we're going to learn that later today. And then we go down. We are looking for binomial. Oops, look at that. Letter A is a binomial, B-I-N-O-M, right? It doesn't have enough space to spell the whole word. Yeah, but that means binomial. Binomial PDF. We also have a binomial CDF. Okay? Yeah. Let me show you when do we use PDF and when do we use CDF. When you are looking for the probability of X assume a specific value, for example, P of X equals 0, or P of X equals 3, or P of X equals 6, when we are looking for the probability of X assume a specific value, we use PDF because the PDF stands for probability density, probability distribution function. Okay, remember what are we looking for in our question? We are looking for, you did not get any question right? So you have 6 questions, you need a guess, and the probability of success is 0.2. We are looking for the probability of X equals 0. Okay, yeah, we are looking for among the 6 trials, you have no success. So let's enter the values. Let's tell the calculator what do we have. Basically, it's the NPX. Okay, N6, we have 6 trials. P is the probability of success, is 0.2. And then, do you see the lowercase x? Yeah, that's why I emphasize the difference between capital letter X and the lowercase x. Because the lowercase x is the value or values assumed by the random variable. Yeah, the random variable need to be written in capital letter. So here x value is 0, right? Here x value is 0. And then you go down and then you paste. Or you have to enter it again. Do you have a 0.262? Yeah, you have more, actually, it's more precise. You have a preciser. Okay, you have preciser answer for this one. If you look at the table, all the values, all the probabilities are already rounded to 3 decimal places, right? But actually, that's enough for us. I mean, if we use a calculator, we have a more precise answer. Yeah, you round it to 3 decimal places, you still have 0.262. It's same with earlier, right? Do you see that, guys? Okay, then let's practice. Thank you. Yeah, let's practice. Help me to find, you guess 6 multiple choice questions, and you get them all right. You get them all right. Yeah, you get all the 6 questions correctly just by guessing. Let's see what's that chance. Use the calculator. Yeah, use the calculator. Of course, you can use the table, right? It doesn't take much time either. Let's see if we can use the calculator to get it done quickly. Just for practice. What do you have? Please don't tell me the chance is 6.4. What's the number the calculator tells us? Yeah, it is. Yeah, exactly. Thank you, Melinda. Yeah, that's what it means. It has e to the power of 95. That means 6.4. Yeah, that decimal 6.4. Move the decimal point. Move the decimal point to the left 5 times. You did great. Yeah, Kelly got the same thing as well. Awesome. You guys great. The same as I have. Okay, very good. So please do answer 64. Okay, 6.4 e to the power 95 means 0.000064. Yeah. So this basically means 6.4 times 10 to the power 95. Kind of like a scientific notation. Yes, scientific notation. That's the way how the calculator handle it. So you have to move the decimal point to the left 5 times. Okay. Yeah. Another thing I want to say, in a binomial distribution, how do we find the probability of at least one quickly? At least one quickly. Think about, we still use the example that we have to talk about the concept. Yeah, we have X represents the number of questions you guess among the 6 questions, among the 6 trials. So all the possible values that the X assume is 0, 1, 2, 3, 4, 5, 6, right? At least one. At least one means what? At least one means exactly 1, or exactly 2, or exactly 3, or exactly 4, or exactly 5, or exactly 6. So it means all those possibilities, right? All those outcomes. Do you agree? That is at least one, correct? Yeah, that is at least one. I want you to tell me what is the complement of at least one. What is the complement of at least one? Yeah, 0. Okay. Yeah. Something I remember to remember that is at the complement of at least one is none. I can type it here. The complement the complement of at least one is none. Pretty catchy, right? Yeah, none means 0. None means 0. Yeah, as you can see, at least one including all those possibilities, then the complement would be x equals 0. All right? Yeah. So can you help me to figure out? We have 6 multiple choice questions. The probability of guess each question right is 0.2. And what's the probability of getting at least one question correctly? Yeah. How do we do that? Do not find the probability of 1 and probability 2, 3, 4, 5, 6 and add them up. Don't do that, please. That's very troublesome. Use the complement. Since the complement of at least one is none, we can write the probability of x is bigger than or equal to 1 as probability of x equals 0. Oh, sorry. We can write it as 1 minus probability of x equals 0. Okay? Yeah, 1 minus. Do you still remember that from the chapter 4? You should, because this week you have to use it for the test. Two events, if two events are complement, then their probabilities add up to 1. So since x is bigger than or equal to 1 is the complement of x equals 0, probability of x is bigger than or equal to 1 equals 1 minus probability of x equals 0, right? Do you see that? Yeah, do you remember what's the probability of x equals 0? I still remember. Is 0.262, right? Yeah. Then you just need to subtract 0.262 from 1 to get a probability of getting at least one success among the 6 trials. Let me know, am I clear about that? Yeah, we use this example to explain the connection between at least 1 and none. All right? Any questions so far? And now let me explain what is a binomial CDF. Yeah, in the manual right below binomial PDF, we have a binomial CDF, right? Yeah, let me explain what does that mean. Binomial CDF gives us the function to calculate, yeah, for a binomial distribution. For a binomial distribution, CDF help us to calculate this probability. X is less than or equal to X at most. Okay, at most. So earlier use the table, we find the probability of at most 3, right? Let's use the calculator to get that done. Unless, can you use a PDF? Yeah, you still can use a PDF. Just find x equals 0, probability of x equals 0, probability of x equals 1, probability of x equals 2, probability of x equals 3, and then add them all up, right? But that's too slow, We don't want to do that. There is a easier way. Probability of x is less than or equal to 3. Let's use a CDF in the calculator. Let's go to second verse again, and then go down to find a binomial CDF. Part B, right? Yeah, capital letter B, binomial CDF. C here means accumulating, okay? C here means accumulating. You accumulate from 0 to 1 to 3 to 2 to 3, yeah. So 6 trials, probability is 0.2, probability of success. And here is the value 3. Yeah, because we have x is less than or equal to 3. So you have to enter 3 here. And then enter. So the probability is 0.983. Do you have the same thing? Yeah. I have a question. What if we need to find the probability of x is less than 3, strictly less than 3? How do you use the CDF function? Then you're going to enter x equals, this is equal to less than or equal to 2, okay? So you can now enter x equals, yeah, exactly. Thank you, Kelly. Perfect. Very good. Question, what if you need to find the probability of x is bigger than or equal to a number? Let's say 2. Is bigger than or equal to, not less than or equal to. And you have to modify this as well. You're going to do, yeah, bigger than or equal to 2 is the complement of x is bigger than, less than or equal to 1, right? Yeah, because all the possible values for x is 0, 1, 2, 3, 4, 5, 6. Bigger than or equal to 2 has a complement less than or equal to 1. So you can use the CDF, enter x equals 1 to find the probability, and then subtract that probability from 1. You see that? So be flexible, use the two functions, either CDF or PDF. It depends on the problem we are solving. You can just play them by using the two functions. All right. Of course, you can use the table for sure. Yeah, table is also very good. I'm just introduce one more method using the technology TI-84 calculator. Are we good with binomial now? Okay, we spent more time than I wanted to, than I planned to. Okay, so let's finish binomial and move on to 6.1, okay? Yeah. In 6.1, we start to talk about continuous random variable. And we cover two types of continuous random variable distribution. The first one is a uniform distribution. The second one is a standard normal distribution. Okay, yeah. Let's look at the notation here. This notation represents the uniform. U is the initial of the word uniform, right? Uniform distribution. For discrete random variable, we have a probability distribution table to describe in detail, to describe the distribution itself. Then what do we have? What kind of tool do we have to study the distribution if the random variable is continuous? Okay, in this chapter we talk about continuous random variable. This specific section, we cover two types of continuous random variable. One is uniform distribution, the other is a standard normal distribution. So for continuous random variable, we have a tool as well. The tool is called density curve. It's a curve, continuous curve, not table anymore, because continuous random variable assume infinitely many and uncountably many values. So table doesn't work anymore. Has to be continuous tool, which is a curve. Let me show you the definition. I think I have this here. Definition of PDF. For continuous random variable, the PDF is different from the PDF we see for binomial. Okay, here means the probability density. The D here is not distribution, it means the density function. Definition of probability density function of a continuous random variable. We use a lowercase f. But we don't have to know that. Important thing is we need to know the density curve. The density curve of a continuous random variable is the graph of the density function. Okay, the density function. For us, the important thing to know about the density curve is to remember a few features about the density curve. Okay, what is the features? The first feature, a density curve A density curve is a curve above the x-axis. When we talk about graph, we are talking about a two-dimensional space. We are talking about a rectangular coordinate system. In a rectangular coordinate system, the density curve has to be above the x-axis. No part is below the x-axis. Okay, that's the first thing. That's the first thing. In order for a curve to be a density curve for a continuous random variable, the first condition needs to be satisfied is the curve has to be above x-axis, no part below x-axis. Second condition, the area below the curve and above the x-axis is 1. Is 1. Yeah, let's write down the two conditions first, and then I'll explain in detail. When we look at a density curve for uniform distribution, and when we look at the density curve for a standard normal distribution. All right? Yeah, the tool we use to study continuous random variable distribution is called the density curve. It is just the graph of the probability density function of the random variable. In order for a curve to be a density curve, two conditions must be, area, exactly, area. I'll explain in a moment. Yeah, two conditions must be satisfied. The first condition is the curve has to completely above x-axis. You know why? Because the probability cannot be negative. That's the reason. Yeah, very similar with distribution table. You know, if we remember the distribution table, all the probability has to be bigger than 0 and less than 1, right? And second condition is all the probability add up to 1. And actually the two conditions for density curve match the two conditions for distribution table. Yeah. The second condition is the area, the region below the curve and above x-axis. The area of the region is 1. Okay, let me explain. Uniform. How do we know if a continuous random variable satisfies a uniform distribution? If we look at its density curve, and its density curve look like this. This is rectangular coordinate system, right? Yeah. Since density curve has to completely above x-axis, we do not really need a lot below the 0. Yeah. So this would be a good example for uniform distribution. Okay. Like that. A horizontal line segment. Yeah, the density curve of a uniform distribution is a horizontal line segment. If the left endpoint is A, right endpoint is B, we say the variable satisfy the uniform distribution on the interval A, B, on the interval from A to B. Okay, yeah, let me fix this part. It's supposed to be vertical. Let's check the two conditions. Let's check the two conditions. First condition, the curve is completely above the x-axis, right? Yeah, very obvious. Second condition is the area. The area of the region right below the density curve and above the x-axis. In this case, of course, it has to be to the right of x equals A and to the left of x equals B, right? This is rectangle. The area of the rectangle has to be 1. The area of the rectangle has to be 1. That's how do we know the height of the line segment is actually 1 over B minus A. Yeah, but that's something extra. We don't have to know. Yeah, because only when the height of the density curve is 1 over B minus A, the area of the rectangle is 1. But as I said, we really don't have to know that because I look at the questions we have here. It doesn't require that. Okay. So once again, yeah, that's the density curve of a uniform distribution. And as I said, the second type of continuous random variable distribution we learned today is called a standard normal distribution. Normal distribution is very important already. And a standard normal distribution is mostly important among all the normal distributions. Since it's so important, we give a specific letter for a variable that is standard normally distributed. We use a Z, capital letter Z, has to be capital letter Z. We use a capital letter Z to represent the variable which follows a standard normal distribution. Okay, and here is the initial of a normal. If we have a normal distribution, the mean is 0, the standard deviation is 1, then the normal distribution is standard normal distribution. Yeah, so that's a notation. Let me show you what's the density curve of a normal distribution, of a standard normal distribution. The density curve of a standard normal distribution look like this. Firstly, the standard normal distribution curve has a 0 as the center. Okay, has a 0 as the center. So it is symmetric. Yeah, so the curve is symmetric with respect to the y-axis. It does not stop like the uniform distribution. So as you can see, I have an arrowhead here, and I also have an arrowhead here. Means it continue to both directions. The x-axis actually is a asymptote, horizontal asymptote of this curve. It's a bell-shaped curve, symmetric with respect to the y-axis because the center of the curve is 0. Center of the curve is 0. So that is the density curve of a standard normally distributed random variable Z. Okay, yeah. Condition 1, the curve is completely above x-axis. Condition 2, this area, the area of this region the area of the region below the curve and right above the x-axis is 1. Believe it or not, is 1. Okay, yeah, it is not diverge, it's converge. Even you might think really it could be 1 because we have basically the right tail is open, right? Even just a little opening is actually open. Yes, it doesn't change the fact the area is 1. Okay, the area is 1. Let me erase that. Am I clear about that? That's what does the standard normal distribution density curve look like. It look like this, all right? Okay, so that's the shape of the density curve for the two types of continuous random variable distributions. One is uniform, the other is a standard normal distribution curve. Distribution. Okay, so now let's focus on finding probability. Okay, how do we find the probability? We're going to learn that by solving problems. Let's look at number 8. Let's look at number 8. Yeah, through those examples, you also get the knowledge what kind of variable actually is uniformly distributed, right? Like a waiting time. When you are waiting on a subway. Yeah, the waiting time actually is uniform distributed. The waiting time between a subway departure schedule and the arrival of a passenger are uniformly distributed. Yeah, the waiting time between a subway departure schedule and the arrival of a passenger. So that means the waiting times between a subway departure and arrival of passenger. That means you go to subway, you have most of the time you have to wait, right? Yeah. That waiting time is a random variable, is a continuous random variable. Sometimes you get lucky, you get it in right away, right? Sometimes you have to wait like 10 minutes. So it's a random variable. And the random variable actually is uniformly distributed between 0 and 7. 0 is make perfect sense, right? At least as I said, sometimes you right away you catch the train right away, so you do not wait. You wait 0 minutes. Sometimes you have to wait longer than that. Seems like this one, the subway, the longest time you need to wait is 7 minutes. 7 minutes. Find the probability that a randomly selected passenger has a waiting time greater than 1.25 minutes. Okay, let's solve this question, okay? You know what? The density curve in this case look like this. A is 0, B is 7, so not AB. Gonna be here is 0, as here is 7. So the density curve is this, from 0 to 7. Density curve from 0 to 7, okay? So we know X follow uniform distribution on the interval 0 to 7. We are looking for the probability that greater than 1.25. So X is strictly greater than, strictly bigger than 1.25. How do we find that probability? On the graph of the density curve, the probability of the variable is bigger than a value or less than a value can be represented by the area. Yeah, let's see, where's 1.25? Yeah, I would say 1.25 is around here, right? 1.25. And the waiting time is strictly bigger than 1.25. That means actually from 1.25 to 7, and that area, that region, the probability can be represented by the area of that region. Does that make any sense? Because the area of the whole rectangle is 1. And the probability that X is bigger than 1.25 can be described by the area of the region below the curve above x-axis, to the right of x equals 1.25 and to the left of 7. Do you think that makes any sense? For a continuous random variable, the probability is found or represented by the area. Because the area of the region below the curve and above x-axis is 1, right? 1 is also a probability 100%. And for the probability of a certain event, we just need to find the region whose area describes the probability, the chance of it occurring. Does that make any sense, guys? Give me some feedback here. Yeah, probably makes sense to some of you, right? Okay, then the probability problem become a geometry problem, right? Yeah, let's see what's the what's the probability that we can find? What's the area of the region? Okay, yeah, what is the area of the region? How do we find that? What is this height? This must be 1 over 7, right? This must be 1 over 7. In order for, yeah, we do need that information. That is 1 over 7. Because the yellow region, let me highlight the yellow region. The yellow region has to be 1. Area has to be 1. So since the length of the rectangle is 7, the height of the rectangle has to be 1 over 7, right? Then the shaded region, I have the stripes. The shaded region would have the area 7 minus 1.25 and then multiply by 1 over 7. Let me do that on my calculator. Let's see if we have the same value. 7 minus 1.25 and then divide by 7. I have 0.8214285,714. Do you have the same thing, guys? Yeah, Leah has the same thing. Yeah. So my calculator tells me 0.821428. Very precise. And we need to round the 3 decimal places as needed. So round it down. We have a 0.821. Can you explain how you got that answer again? Yeah, very good. Yeah, so we do have to know the height of the curve, okay? We do have to know the height of the curve. I don't know if you can see the yellow region that I highlighted. The yellow region is a region below the density curve above x-axis from 0 to 7, right? That region is supposed to have area 1. That region supposed to have area 1. Since the length of the rectangle is 7 from 0 to 7, in order for the area to be 1, the height has to be the reciprocal of the length. Since the length is 7, the height has to be 1 over 7. Then length times the height, or base times the height, is 7 times 1 over 7. That gives us the area 1. Right, Miranda? So we do need to know the height is 1 over 7. Yeah, so now we know the height is 1 over 7. And what we want to find is the area of this gridded region, right? The gridded region. The gridded region has a base 7 minus 1.25, has a height 1 over 7. So the gridded region also is a rectangle. The area of the rectangle is the base times height. So 7 minus 1.25 is the base, 1 over 7 is the height. So multiply them together, use the calculator, we have the probability. Yes or no? Does that make sense? Let's try one more. Yeah, let's try one more. Number 9 is also about uniform, okay? Let's see if I can make more space. I need more space to write things. Okay, let me just do this. Okay, number 9. A statistics professor plans classes so carefully that the lengths of her classes are uniformly distributed. Like a subway schedule, that means good, right? Very consistent. Are uniformly distributed between 45 and 55 minutes. Okay, so here we have a random variable, continuous random variable, follow uniform distribution on the interval 45 minutes to 55 minutes. That's what we have, right? Okay, sorry, it's closed. Some book use open. I'll explain. Actually, it doesn't matter. Okay, so I'll explain in a minute. We need to find a probability that a given class period runs between 50.5 and 51.5. That's what we want, right? Yeah, that's the probability we are trying to find. Yeah, X is uniform distributed. We are looking for the probability that X is bigger than 50.5 and then less than 51.5. Okay, so let's see how do we do that. Okay, I would draw the curve first. The uniform distribution is from 45 to 55. Just you know, let's say this is 45, this is 55, right? And the curve is this high. Not very accurate, by the way. Just a draft. Yeah. Anybody can help me to figure out what's the height of the line segment? You are looking at a yellow rectangle, right? Yeah. Can you tell me what's the base of the yellow rectangle? Or what's the length of the yellow rectangle? 10? Yeah, exactly. And what's the height of the rectangle supposed to be? Yeah, 1 over 10. Exactly, 1 over 10. Perfect. Yeah, so we're 0.1, right? Yeah, either 1.1 over 10 or 0.1. Okay, and we are looking for X is between 50.5 and 51.5. We are looking for this tiny rectangle. We are looking for that area, right? Yeah, from 50.5 to 51.5. Okay, help me to figure out the area. Help me to figure out the area. What's the base of that area? Base word. Yeah, the base. In this case, gonna be width. What's the base? Not 10 anymore. I mean the black rectangle, not yellow. Do you see the shaded region is a is 1. Yeah, thank you, Kelly. Is 1. Very good. The base is 1. What is the height? What is the height? 10. Yeah, 1 over 10. 1 over 10. Very good. So the probability is 1 times 1 over 10, or 0.1, right? And that's it. Yeah, I look at the calculator. I do not see the distribution for uniform. So we would have to manually calculate like what I did for those 2 examples. Yeah, probably we don't need. Yeah, it's really just to finding the area of a rectangle. I hope after those 2 questions, we have a good understanding. We can solve the similar problems. Yeah, if we are given a continuous random variable whose distribution is a uniform distribution on a certain interval, how do we find the probability of the random variable fall in a certain region, certain range? All right. One more thing before we keep going. Yeah, I have a question. What if I want you to find the probability of x is strictly bigger than that, strictly less than that, or x is bigger than or equal to 50.5, strictly less than 51.5, or strictly bigger than 50.5 and less than or equal to 51.5. Do you see what I'm talking about? What if I change the inequality symbols from less than or equal to strictly less than? Change both or just change one of them? Would that change anything? Would that change the value of the probability? Would that change the value of the probability? It wouldn't be the same. Yeah, exactly. Thank you, Dustin. Yeah, how do we explain it would be the same? Because the area stays the same, okay? The area of the region stays the same. Because in the two-dimensional space, the area of a line is 0, okay? So you include this edge or not include this edge, really doesn't matter. It does not change the value of the area. That's very good. That's very good that you see that. Okay, we don't have much time, but let's see something about standard normal distribution. Then you can start to work on the problems. Okay, 6.1. I introduced the density curve for a standard normal distribution. Just something quickly to introduce. What kind of variable is normally distributed? Yeah, normal distribution is so common in real world. What type of random variable is normally distributed, right? Okay, if a random variable consists of many factors, yeah, many factors contribute to the variable, but none of the factors is dominating. Each of them would contribute a little bit, and the whole combination of those factors give the random variable x, but none of the factors dominating, then that random variable is normally distributed. Okay, so we have a lot of examples for normal distribution in real world. For example, height of people, weight of people, blood pressure, yeah, a lot of biological thing, right? Blood pressure of people, pulse rate of people, even salary of people, or IQ scores, right? Yeah, all those things are normally distributed. Because if you think about each single of them, they are a combination. Yeah, each single of them, it is a combination of many different factors, and each factor contribute to the variable, but none of them is dominating. Yeah, then that kind of variable is normally distributed. Then what is a standard normal distribution? Standard normal distribution has mean equals 0 and a standard deviation equals 1. Okay, yeah. Standard normal distribution has a mean equals 0 and a standard deviation equals 1. That's how you see right here the notation. Mean is 0, standard deviation is 1. Okay, yeah, and the curve we see right now is a standard normal distribution density curve. Okay, let's see this question. It is number 10. Number 10. We are given a standard normal distribution curve. Sometimes I'll just say Z curve. Instead of saying the 3 words, standard normal distribution curve, I'll just say Z curve. Z curve means the standard normal distribution curve, okay? By the way, it looks like it's closed, but no, it's not closed, okay? It's open. It's just not very accurate. What are we looking for? We are looking for the area of the shaded region we are looking for area of the shaded region. So knowing the capital Z, capital letter Z represents the standard normally distributed random variable. The lowercase z represents the value that the capital Z assume. Okay, yeah. So basically, we are looking for the probability of Z less than or equal to, really doesn't matter as we mentioned, right? Yes, strictly less than 0.69 or less than or equal to 0.69. It doesn't change the probability. Yeah, we are looking for this probability, and that probability can be represented by the shaded region. Yeah, suppose this is 0.69. That makes sense because 0 is here, right? So 0.69 must be on the right side of the center, on the right side of the center. Yeah, how do we find that probability? I'm going to use two different methods. The first method, we use the table. The second method, we use the TI-84 calculator. The first method, the table, since your z-score here, yeah, we also call the 0.69, the z-score is positive. We are going to look at, yeah, remember, let's write it down. The z-score is 0.69. Z-score is 0.69, okay? Yeah, we are looking for the probability that Z is less than 0.69. Let's remember that, yeah, because we are going to look at the table now. We have two tables. This one is a negative z-score. So as you can see, the z-score is on the left-hand side of the center, right? Center is 0. But our case, our z-score is not negative. Our z-score is a positive 0.69. So we're going to go to the other table. The other table is a positive z-score, okay? Yeah, as you can see, the z here is to the right of 0, okay? All right, so you can see a bunch of numbers on the table. Those are probabilities, yeah. And what we need to look for is the z-score. And this edge has the first digit to the right of the decimal point. To the right of the decimal, we have the z-score rounded to one decimal places. So we have a 0.69. So we are looking for 0.6. We are looking for 0.6. 0.6 is right here, right? Yeah. And what about 9? 0.69 is our z-score. So we have a 0.6. We are missing 0.09, right? Do you agree? We are missing 0.09. Because 0.69 is 0.6. 0.69 is 0.6 plus 0.09. The hundredth. 0.69 is 0.6 plus 0.09. So we already have a 0.6 right here. And we need to find a 0.09 on the top. Okay? On the top, we have a 0.00, 0.01, 0.02, 0.03, all the way to 0.09. So that's our 0.09. Okay. 0.6, 9. What's the intersection? What is the probability here? Can you spot it? Oh, awesome. And it's already rounded. Rounded to the nearest, what is that? Tens, hundreds, thousands, 10,000s, 4 decimal places. And that's how do we find the area of that region. Okay? Yeah. And you know what? We can use a TI-84 calculator to get that done even faster. I'm not forcing you to get one, but if you don't have one, you use the table. The table is also good. But if you can have a TI-84 calculator, is also good, okay? In your TI-84 calculator, go to second similar with the binomial. You have to push this because it's too bright. It's too bright. So we go to second. Second is here. VARS is here. And you turn on your calculator and then you enter second VARS. You would have this distribution table, right? A distribution list. Yeah, we actually had that earlier. And you see the first two, yeah, how important the normal distribution is. The first two is about normal distribution. And in this case, we always use, in what case? In the case of normal distribution, we always use normal CDF. If you need to take a note, please take a note. In the case of normal distribution, the technology in TI-84 calculator, we only use number 2, normal CDF, cumulative distribution function. We do not use a PDF. Okay, we only use the CDF. Only use the CDF. I'll continue repeating that. Okay, CDF. And the lower our graph, you see the we actually can see the graph here, right? You see the left endpoint, like the region start from negative infinity, right? Yeah, on the calculator, negative E99 is negative infinity. It's already there. Yeah, if it's not there, how do you enter yourself? You need to pay attention here. Negative on the calculator is not a minus sign. Please don't use that. You're gonna struggle. I always get an error, always get an error. You know why? Because that's not negative, that's a minus. In order to enter negative, you need to use this key in the parentheses. That is a negative, okay? Yeah, you can enter that manually, negative. And then how do you find the E? The E, please remember, is the second comma. Second is here, comma is here. Okay, comma is right above 7. Comma is here. So you actually see it as double E. But double E on the screen of the calculator is only 1 E. So negative, second comma, and you would see negative E, right? You don't see double E, but actually you enter double E. So and 99. That's how do you enter negative infinity. Yeah, negative infinity, so look at our curve, look at our region. From negative infinity to 0.69, right? So the lower.
Hey, Professor, I think you need to hit a 1 as well. Professor?
0.69.
Professor Betty?
And then keep mu equals 0, sigma equals 1. I think you need to
hit a 1 as well.
Because it's defaulted as standard normal, and we are dealing with a standard normal, so keep it. Next time we would use a different mu, different sigma. So this time mu is 0, sigma is 1 because it's standard. And then paste. Do we have the same value with the table result? 0.7549, right? If we round it to keep 4 decimal places. Am I clear, guys? Sorry, wasting your 5 minutes. we supposed to finish 5 minutes ago. But it's very useful what I teach the last 5 minutes, right? We're gonna continue using both table and TI-84 calculator to find either the probability of the standard normally distributed variable fall between a certain range, or we are given the probability, we need to find a corresponding z-score. Yeah, we're gonna get that done Tuesday. Okay. Yeah, this week, besides you understand what we have learned on in the class and still catch up your homework, the main thing is to focus on your tests. We have a lot of people finished today, but a lot more people not finished the test yet. So you have tomorrow, the last day. Yeah, let me know if you have anything that need help for me. Yeah, just email me. We're gonna stop here. Let me take a picture of the attendance. Interesting is sometimes it shows the same number of people, but the people in the list are different. Yeah, let me take a picture. Okay, we're done today. Thank you guys for coming. I'll say good night and see you on Tuesday.